Let zeta be a primitive nth root of 1. Zeta is e to the 2 pi I over n. The field Q of zeta is called cyclotomic field. Clearly, this field contains all nth roots of unity. So we have 1 zeta, zeta squared, up to zeta to the power n minus 1. All, of course, belong to Q of zeta. And these are the roots of a polynomial x to the power n minus 1. So we conclude that Q of zeta is a splitting field of x to the n minus 1. So this tells us that this field is the Galois extension of Q. Nth roots of unity split the unit circle in the complex plane into n equal parts. And for this reason, this field is called cyclotomic. So this means splitting the circle. Since we have a Galois extension here, we can consider the Galois group. Let sigma be an element of the Galois group of Q of zeta over Q. Then sigma is completely determined by its action on zeta, because zeta is generator of this field. Moreover, sigma must permute the roots of the polynomial x to the n minus 1. This tells us that sigma of zeta must be another nth root of unity, so it can be written as zeta to the power a for some a. Clearly, not every value of a is admissible here. So, for example, a equals 0 is not allowed because zeta cannot possibly be mapped to 1. We need to determine the values of a for which this action of sigma induces a permutation of the roots of x to the n minus 1. Consider another mapping tau such that tau of zeta is zeta to the power b. Let us compute the composition. So what is tau of sigma of zeta? So here we have tau of zeta to the power a, and since tau is a ring homomorphism, so this is equal to tau of zeta to the power of a, or zeta to the power ab. So we have that sigma is an automorphism if and only if sigma is invertible. Suppose tau is the inverse of sigma. Let us determine what are the conditions on A and B such that the composition of tau with sigma is identity. And then we see that tau is the inverse of sigma if and only if A times B is equal to 1 mod n. We can see here that for each element of the Galois group, we can associate a remainder mod n. And the group structure on the Galois group is multiplicative, which can be seen from this composition formula. And then finally, we conclude that the Galois group of a cyclotomic field is just the multiplicative group of remainders mod n. And the remainder A belongs to this group if and only if it's relatively prime to the modulus n. So we point out that this group is abelian. Let us see what will happen if we join to Q two distinct roots of unity. Let zeta 1 be e to the 2 pi I over n, and zeta 2 be e to the 2 pi I over k. And consider the field Q with zeta 1 and zeta 2. To understand this field, we take multiplicative subgroups generated by these two complex numbers. So let Zi be multiplicative subgroup in C star generated by zeta I. Of course, we have that Z1 is isomorphic to Zn and Z2 is isomorphic to Zk. Moreover, these two subgroups are subgroups in a unit circle. So these sit in S1, which is complex number Z, such that norm of Z is equal to 1. Or this can be also described as exponential e to the I alpha, where alpha belongs to real numbers. Consider the product of these two subgroups, Z1 times Z2. So this will be a multiplicative subgroup generated by both zeta 1 and zeta 2. This will be again a finite subgroup in S1. And it's easy to see that any finite subgroup in S1 is cyclic. To prove this, choose an element in this subgroup so e to the I alpha with the smallest positive alpha. And then, using division with remainder, we see that the argument of any other exponential in this subgroup must be a multiple of alpha. And then we see that the value of alpha for the generator of this subgroup must have the property that 2 pi over n is a multiple of alpha, and 2 pi over k is also a multiple of alpha. And then it's easy to see that Z1 times Z2 is generated by e to the 2 pi I over m, where m is the least common multiple of n and k. And then from here we see that the field obtained from Q by adjoining zeta 1 and zeta 2 is again a cyclotomic field, which is generated by e to the 2 pi I over m, where m is this least common multiple. Likewise, if we add to Q several distinct roots of unity, the result will be still a cyclotomic field. The primary mission of algebra is solving various sorts of equations. In some form, people knew how to solve quadratic equations since Babylonian times. So 2000 BC. We also have formulas for solving cubic equations and quartic equations, the equations of degree 4. The formulas for solving such polynomial equations were discovered only in Renaissance Italy in 16th century. For cubic equations, this was found by Del Ferro, who kept his formula secret for most of his life and revealed it only on deathbed to one of his students. And it was published in a more general form by Cardano. The formula for the solution of cubic equations is much more complicated than the formula for the quadratic equations. And for the quartic equations, the formula is even more complicated. So it is very impressive that Italian mathematicians were able to find these formulas. For quartic equations, this formula was found by a student of Cardano, Ferrari, and again published by Cardano. These formulas also stimulated the development of complex numbers, because one needs to carry out computations in complex numbers, even in the case when all the roots of such a polynomial equations are real. So this was done in 16th century. For a long time, people tried to generalize these formulas to equations of degree 5. These attempts continued until 19th century, when Lagrange, Abel, and Galois were able to show that no such formula exists. To prove this theorem, it was necessary to develop both group theory and Galois theory. This theorem should not be viewed as just a negative fact. The methods developed for this proof also allow us to systematically derive the formulas of Cardano for cubic and quartic equations. Also, for some equations of degree 5 and higher, there is a formula, and this theory allows us to write down the algebraic expressions for the roots of higher degree polynomials whenever it is possible. Proving impossibility of giving algebraic solutions to equations of degree 5 and higher is the next big goal in this course. Let us begin by understanding the exact statement of this theorem. In the formulas that we discussed above, in addition to 4 basic arithmetic operations, we use the operations of extracting nth roots. So these are called radicals. Let's consider an example. So what does it mean that a number is expressible in radicals? So if we take alpha to be square root of 2 plus fifth root of 1 plus cube root of 3. And now we want to consider extensions of Q by adjoining numbers that are expressible in radicals. We generalize the notion of a number which is expressible in radicals in the following way. We give the following definition. An extension f of the field of rational numbers is called a radical extension if there exists a chain of field extensions of Q. So we have Q, which is E0, which sits in E1, in E2, and so on in En, such that each field Ek, so for k from 1 to n, the field Ek is the extension of Ek minus 1 with an element alpha k, where alpha k to the power mk belongs to Ek minus 1 for some mk in n. And with the condition that the field f is a subfield in the last field in this chain. Here, if we just denote alpha k to the power mk as beta k, then the field Ek may be thought of as an extension of Ek minus 1 with the root of degree mk of beta k. This second equality should be viewed as just something informal because of the ambiguity due to the fact that the operation of extracting roots is in general multivalued. If we go back to our example, where we take alpha to be square root of 2 plus fifth root of 1 plus cube root of 3, then here we could consider the following chain of field extensions. So we have q, then we take q with a joint square root of 2, then we have q with a joint square root of 2 and cube root of 3, and finally we take q with a joint square root of 2, cube root of 3, and fifth root of 1 plus cube root of 3. And then we will have that the extension of q with element alpha is a subfield in the last field in this chain. So q of alpha is a radical extension of the field of rational numbers. Our next big goal in this course is proving the following theorem. Let E be a Galois extension of rational numbers. Then E is radical if and only if the Galois group of E over Q is a solvable group. It's precisely this theorem that explains why solvable groups are called solvable. If we take a polynomial with rational coefficients, then this theorem says that the roots of this polynomial are expressible in terms of radical if and only if the Galois group of the splitting field of this polynomial is a solvable group. Using this theorem, we will construct polynomials whose roots are not expressible in terms of radicals. All we will have to do is to compute the Galois group corresponding to these polynomials and show that these Galois groups are not solvable. When proving this theorem, we will find that it is more convenient to work with the cyclotomic field in place of the field of rational numbers. This will be our step 1. We want to show that we can replace in the statements of this theorem Q with the field K, which is Q of zeta, the cyclotomic field. Let us show that this can be indeed done. First, we remark that Q of zeta is a radical extension of Q. So indeed, zeta informally is the nth root of 1. Or more formally, so we can write that zeta to the power n is equal to 1, which is an element of rational numbers. So by definition, this is a radical extension of Q. Next, we have the following simple lemma. Let K prime and K double prime be two extensions of Q. Then the product K prime times K double prime is radical if and only if both K prime and K double prime are radical. Now, the proof of this lemma is pretty obvious. So we construct the chains of field extensions for K prime and for K double prime. So we have Q which is E0, which sits in E1 with the prime, in E2, and in En with the prime, such that Ei prime is Ei minus 1 prime with an element alpha I prime, and the field K prime being a subfield in the last field En prime. Likewise, we have another chain. So Q is E0 double prime, which sits in E1 double prime, in E2 double prime, and so on with Em double prime, such that Ei double prime is Ei minus 1 double prime extended with alpha I double prime. And K double prime sits in Em double prime. Now we can put these two chains into one longer chain. So we will have that Q is contained in E1 prime, is contained in En prime, and then we take En prime with the joint alpha 1 double prime. And then this is contained in En prime with the joint alpha 1 double prime and alpha 2 double prime. And so on until we'll come to En prime with the joint all alphas double primes. And then we will have that the product K prime, K double prime is a subfield in this last field, in this chain. So we get the following claim, that if K prime and K double prime are radical, then their product K prime times K double prime is also radical. For the converse, we note that a subfield in a radical extension of Q is radical. And of course, K prime and K double prime are both subfields in the product K prime times K double prime. As a corollary, we get the following claim, that let K be a cyclotomic field and E is an extension of Q. Then E is radical if and only if K times E is radical. Next, let us prove the following proposition. Let K be a cyclotomic field and let the extension E of Q be Galois. Then the extension KE of the field K is Galois, and the Galois group of E over Q is solvable if and only if the Galois group of KE over K is solvable. To prove this proposition, we recall two results that we have already established in this course. The first result concerns this diagram of fields. We already proved that if the extension E is Galois, then KE is Galois over K for any field K. And so we recall that the Galois group of KE over K is in fact isomorphic to the Galois group of E over the intersection of E with K. The second fact that we will need is from group theory. And so if H is a normal subgroup in a group G, then G is solvable if and only if both H and the quotient group G by H are solvable. Now, assume that the Galois group of E over Q is solvable. Then this implies that the Galois group of E over the intersection of K with E is also solvable, since a subgroup in a solvable group is solvable. And the Galois group of E over K intersected with E is a subgroup in the Galois group of E over Q. And this tells us that the Galois group of EK over K is solvable, since these two groups are isomorphic. Now let's assume that the Galois group of EK over K is solvable. This tells us that the Galois group of E over the intersection E with K is solvable, since these two groups are isomorphic. Then we note that the extension E intersected with K is normal. Indeed, if we have a homomorphism sigma from E intersected with K into Q bar, then since both E and K are normal, we will have that sigma of E is equal to E, sigma of K is equal to K, and this tells us that sigma of the intersection is equal to the intersection. This tells us that the Galois group of E over E intersected with K is normal in the Galois group of E over Q. And the Galois group of E intersected with K over Q is isomorphic to the Galois group of E over Q, quotient by the Galois group of E over E intersected with K. Likewise, the same Galois group is isomorphic to the quotient of the Galois group of K over Q by the normal subgroup Galois group of K over the intersection. But the field K here is cyclotomic. And we saw that the Galois group of K over Q is abelian. So this tells us that the Galois group of E intersected with K over Q is also abelian, because the quotient of an abelian group is abelian. Now we see that the Galois group of E over Q has a solvable normal subgroup. So this Galois group of E over intersection of E with K is solvable. And the quotient is abelian and thus solvable. And this implies that the whole group, so the Galois of E over Q, is solvable. And this completes the proof of the proposition. Now, with what we have proved, we can see that we can restate our goal theorem in the following way. So, equivalently, we can say that let E be Galois and let K be a cyclotomic field. Then the field KE is radical if and only if the Galois group of KE over K is solvable. We proved that KE is radical if and only if E is radical, and the Galois group of KE over K is solvable if and only if the Galois group of E over Q is solvable. Hence, this main theorem can be restated in the following way, and we shall see that replacing the base field Q to the cyclotomic field will simplify our calculations and our proof.